Welcome to the world of solid-state physics. Today, we'll explore the band theory of solids, a fundamental concept that explains how electrons behave in different materials. The band theory is crucial in understanding why some materials conduct electricity while others don't. By examining the energy levels available to electrons, we can unravel the mysteries of electrical and thermal properties of solids. Think of it as a roadmap that helps us understand how electrons move and interact within a material's atomic structure. The band theory provides insights into the fundamental behavior of electrons, revealing the hidden world of energy bands and electron mobility. Let's dive into how energy bands are formed in solid materials. Imagine atoms as individual musicians, each playing their own unique note. When these atoms come together to form a solid, something magical happens. Their atomic orbitals start to overlap and interact. In isolated atoms, electrons exist at discrete, quantized energy levels. But when atoms join forces, these energy levels begin to merge and split due to interactions between neighboring atoms. As more atoms join this atomic ensemble, these energy levels become so closely spaced that they form continuous energy bands. It's like individual musical notes blending into a harmonious symphony of electron energy states. In the world of solids, we have three key players: the valence band, conduction band, and band gap. The valence band contains electrons involved in atomic bonding, typically bound to atoms and not contributing to electrical conductivity. The conduction band is where electrons are free to roam throughout the solid, like tourists exploring a new city. When electrons in the valence band gain sufficient energy through thermal excitation or light absorption, they can jump into the conduction band, enabling electrical conductivity. The band gap represents the energy difference between these two bands. Different materials have different band gap sizes, which determines their electrical properties, whether they're conductors, semiconductors, or insulators. In a solid, electrons don't move freely, but dance to the rhythm of a periodic potential created by regularly spaced atoms. Bloch's theorem provides the musical score for this electron dance, stating that electrons will have wave functions modulated by a periodic function. The Kronig-Penney model helps us visualize this complex movement. Imagine electrons navigating through a landscape of atomic potential wells, where their motion is constrained and defined by the crystal's periodic structure. This periodic potential significantly influences the allowed energy states of electrons, making their movement more structured and predictable than in free space. The Kronig-Penney model is a simplified theoretical approach to understanding electron behavior in a periodic potential. It treats the solid as a one-dimensional system with a regular, periodic potential that mimics the crystal lattice. The model assumes electrons are essentially free particles, moving within a potential that alternates between finite and zero values. This idealized square well potential represents the regular atomic positions in a crystal. By breaking down electron motion into this simplified framework, scientists can gain fundamental insights into how electrons interact within a structured, periodic environment. Let's explore the intricacies of the Kronig-Penney model's periodic potential. In this model, the potential function repeats at regular intervals, creating a mathematical representation of a crystal's atomic structure. The potential is defined within specific parameters, with a width representing the potential well and a defined potential depth. Electrons in this model are treated as wave-like particles, described by the Schrödinger equation. The wave function changes behavior depending on the potential, behaving like a free particle where potential is zero, and being affected differently within potential wells. This approach helps us understand how electrons move and interact within a structured crystal environment. In this slide, we'll dive deeper into the energy bands and gaps created by the periodic potential. The chronic penny model reveals how electron energy levels split into allowed and forbidden bands. Certain energy ranges become regions where electrons can exist, corresponding to valence and conduction bands. Between these bands, we find band gaps, regions where electrons cannot exist. The periodicity of the potential also leads to the formation of Brillouin zones, which are special regions in momentum space where allowed electron states exist. This concept helps us understand how electron energy is not continuous, but quantized in specific bands. The Miller indices, denoted as HKL, describe the orientation of planes in a crystal lattice. To determine these indices, follow these steps. Find where the plane intersects the crystallographic axis in terms of the unit cell dimensions. Take the reciprocals of these intercepts. Multiply by a common factor to convert the reciprocals into the smallest set of integers. For example, if a plane intersects the x-axis at A, the y-axis at B, and the z-axis at C, the resulting Miller indices are calculated as H equals 1 divided by A, K equals 1 divided by B, L equals 1 divided by C. These integers H, K, and L represent the orientation of the plane within the crystal lattice. Let's explore the fundamental building blocks of crystal structures. We have three primary simple crystal structures: simple cubic, body-centered cubic, and face-centered cubic. In the simple cubic structure, atoms sit at cube corners. It's the most basic arrangement but rare in nature due to low packing efficiency. Body-centered cubic adds an atom at the cube center, found in metals like iron and chromium. Face-centered cubic, with atoms at corners and face centers, is highly efficient and common in metals like aluminum and gold. Each structure has unique characteristics like coordination number and atomic packing factor that determine their physical properties. The chronic penny model provides fascinating insights into electron behavior in solids. It predicts the formation of discrete energy bands where electrons can exist, separated by band gaps where no electron states are allowed. This explains the fundamental differences between conductors, semiconductors, and insulators. In conductors, the conduction band overlaps with the valence band, allowing free electron movement. Insulators have a large band gap preventing electron movement. Semiconductors sit in between, with a small band gap that allows limited electron movement under specific conditions. This model helps us understand how material structure determines electrical conductivity. Visualizing electron behavior becomes fascinating when we compare free electrons to electrons in a periodic potential. In the absence of a periodic potential, an electron's energy is continuous, and its wave function appears smooth and sinusoidal. However, when a periodic potential is introduced, something remarkable happens. The electron's wave function splits into multiple allowed bands and gaps, creating a complex energy structure. This transformation reveals how the periodic arrangement of atoms fundamentally changes electron movement. The resulting energy band structure mirrors real-world solid materials, explaining why some materials conduct electricity while others don't. Brillouin zones are unique regions of momentum space critical to understanding electron wave properties in crystalline solids. Think of them as special maps that show where electrons can potentially exist. The first Brillouin zone contains all possible wave vectors for electrons in a crystal lattice. It's defined using the Wigner-Seitz construction in reciprocal space, a mathematical way of describing the crystal's periodicity. Imagine these zones as exclusive territories where electrons are allowed to travel, with each zone representing different energy states. The shape and size of Brillouin zones depend entirely on the crystal lattice's symmetry. Brillouin zones are more than just spatial regions. They're fundamental to understanding electron behavior. The first Brillouin zone corresponds to the allowed electron states in a crystal. As we move to higher-order zones, we encounter increasingly restricted regions separated by forbidden areas called band gaps. Each zone's size and shape directly reflect the crystal lattice's symmetry. In a simple cubic lattice, the Brillouin zone looks like a cube, while a hexagonal lattice creates a hexagonal-shaped zone. These zones are crucial for describing energy bands, helping scientists understand how electrons move and interact within different material structures. The role of Brillouin zones extends deep into solid-state physics. They are essential for mapping electron band structures, showing exactly where electrons can and cannot exist within a crystal. The first Brillouin zone contains the lowest energy wave vectors, while subsequent zones represent higher energy states. Electrons are restricted to moving within these zones, making them critical for understanding material conductivity. By defining allowed and forbidden regions, Brillouin zones help explain why materials behave differently electrically. They're like traffic maps for electrons, guiding their potential paths through the crystal's complex energy landscape. The effective mass of electrons is a crucial concept in solid-state physics. It describes how electrons behave under the influence of an applied force within a periodic potential, such as a crystal lattice. The effective mass reflects the dynamics of electrons, simplifying the complex interactions within the material. The effective mass of an electron in a periodic potential quantifies how an electron behaves under an external force, accounting for interactions within the crystal lattice. In a periodic potential, electrons do not behave like free particles. The periodic structure modifies their motion. Mathematically, the effective mass, denoted as m star, is given by the relation 1 divided by m star equals 1 divided by the reduced Planck's constant squared, multiplied by the second derivative of energy, E, with respect to the wave vector, k. In words, this involves taking the reciprocal of the effective mass, which equals the reciprocal of the reduced Planck's constant squared, multiplied by the curvature of the energy band. This effective mass helps in understanding the electron dynamics and the transport properties of materials. Effective mass is a fascinating concept that describes how electrons respond to external forces within a crystal lattice. Unlike a free electron's mass, effective mass changes based on the energy band's curvature. When the band's curvature is small, electrons move slowly, representing a large effective mass. Conversely, a high curvature means electrons move more easily, indicating a smaller effective mass. In semiconductors, this concept is particularly important. The effective mass affects electron mobility, influencing the material's electrical conductivity. Different regions of the conduction band can have varying effective masses, adding complexity to electron behavior. Energy band structures are the cornerstone of understanding material properties in solid-state physics. They determine how electrons are distributed within a solid and explain the fundamental differences between metals, semiconductors, and insulators. By examining the arrangement of electron energy levels and the presence or absence of band gaps, we can predict a material's electrical and optical characteristics. This fascinating concept reveals why some materials conduct electricity effortlessly, while others resist electron flow. The energy band structure is like a blueprint that explains the fundamental electronic behavior of different materials. In metals, The energy band structure is uniquely characterized by overlapping valence and conduction bands. This overlap means electrons can move freely between bands, creating exceptional electrical conductivity. The Fermi level in metals lies within or at the boundary of the conduction band, allowing electrons to be easily excited into freely moving states. Take metals like copper or aluminum, where there's practically no band gap. This means electrons can flow with minimal resistance, making metals excellent conductors. The free electrons in the conduction band are responsible for metals' high electrical and thermal conductivity. Semiconductors occupy a unique position in the world of electrical conductivity. They have a small band gap between the valence and conduction bands, typically around 1 electron volt for silicon. This narrow gap allows electrons to be excited across the band at room temperature or higher, enabling controlled conductivity. Unlike metals, semiconductors require some external energy to move electrons between bands. This characteristic makes them incredibly versatile for electronic applications. Materials like silicon and germanium can conduct electricity under specific conditions, making them fundamental to modern electronics and semiconductor devices. Insulators represent the opposite end of the electrical conductivity spectrum. They feature a wide band gap between the valence and conduction bands, typically greater than 3 electron volts. This substantial energy barrier prevents electrons from moving between bands under normal conditions. Materials like diamond and glass exemplify perfect insulators. The large band gap means electrons cannot easily transition to the conduction band, resulting in extremely low electrical conductivity. Only under extreme conditions like very high temperatures or massive electric fields might insulators show any hint of conductivity. Let's recap the key differences in energy band structures across material types. Metals showcase no or minimal band gaps, allowing electrons to move freely and creating excellent conductivity. Semiconductors have small band gaps between 0.1 and 2 electron volts, enabling controlled conductivity that depends on temperature and doping. Insulators feature large band gaps exceeding 3 electron volts, preventing electron movement and resulting in poor conductivity. This fundamental classification explains why different materials behave so distinctly when it comes to electrical conduction, providing insights into their unique electronic properties. Intrinsic semiconductors are pure semiconductor materials without significant impurities. Composed of single elements like silicon or germanium, these materials have unique charge carrier characteristics. At absolute zero temperature, they have no free charge carriers. As temperature increases, electrons gain enough energy to jump from the valence band to the conduction band, creating electron-hole pairs. Their electrical conductivity remains relatively low compared to metals. The Fermi energy in intrinsic semiconductors sits roughly in the middle of the band gap, representing a delicate balance between the valence and conduction bands. Extrinsic semiconductors are created by intentionally introducing impurities to modify electrical properties. This doping process increases the number of charge carriers, making the material more conductive. By adding specific impurities, we can dramatically alter the semiconductor's behavior. The goal is to enhance electrical characteristics by deliberately manipulating the material's electronic structure. Doping transforms a pure semiconductor into a more versatile electronic component, opening up possibilities for advanced electronic applications. In N-type semiconductors, donor impurities from group V elements like phosphorus are introduced into the semiconductor, typically silicon. These donor atoms provide extra electrons in the conduction band, increasing free electron availability. Electrons become the majority charge carriers, while holes remain the minority carriers. The Fermi energy shifts closer to the conduction band, reflecting the increased electron density. This process creates a semiconductor with enhanced electrical conductivity, where electrons are the primary charge transport mechanism. P-type semiconductors are created by introducing acceptor impurities, typically from group 3 elements like boron and silicon. These impurities create holes in the valence band, which act as positive charge carriers. In this configuration, holes become the majority charge carriers, with electrons as the minority carriers. The Fermi energy moves closer to the valence band, indicating the increased presence of holes. This doping strategy transforms the semiconductor's electrical properties, enabling controlled conductivity through hole movement. Doping fundamentally alters the Fermi energy in semiconductors. In undoped semiconductors, the Fermi level sits near the center of the band gap. When doped with N-type impurities, the Fermi level shifts closer to the conduction band due to additional free electrons. Conversely, P-type doping moves the Fermi level closer to the valence band because of hole creation. This shift indicates the probability of electron energy state occupation at absolute zero temperature. Doping essentially provides a precise mechanism to control a semiconductor's electrical conductivity by manipulating its energy levels. A p-n junction forms when a p-type semiconductor meets an n-type semiconductor, creating a fundamental building block in semiconductor devices. Before contact, the p-type region is rich in holes, while the n-type region is abundant with electrons. When these two regions meet, something remarkable happens. Electrons from the n-side diffuse into the p-side, and holes from the p-side move into the n-side. This migration creates a special region called the depletion region, where free charge carriers are absent. An electric field is established, setting the stage for fascinating electronic interactions. The energy band diagram of a p-n junction reveals a complex interaction between two semiconductor types. When p-type and n-type materials come into contact, their conduction and valence bands align differently. The conduction band and valence band of the p-side sit at a higher energy compared to the n-side. The Fermi level remains constant across the junction, creating a built-in potential barrier. This energy difference is crucial in determining how charge carriers move and interact at the junction, forming the basis for many semiconductor devices like diodes and transistors. In an unbiased p-n junction, no external voltage is applied. The built-in potential barrier prevents charge carriers from freely moving across the junction. The depletion region forms naturally, with no current flowing between the p and n regions. This state represents the junction's equilibrium condition, where the electric field created by the diffusion of charge carriers balances out. Think of it as a gate that remains closed, preventing the free movement of electrons and holes between the two semiconductor regions. Forward biasing occurs when the positive terminal is connected to the p-side and the negative terminal to the n-side. This applied voltage reduces the width of the depletion region, creating a pathway for charge carriers to move across the junction. As the voltage increases, current begins to flow, increasing exponentially after overcoming the potential barrier. It's like removing obstacles and opening a gate, allowing electrons and holes to flow more freely between the p and n regions. This characteristic makes forward-biased p-n junctions essential in many electronic components. In a reverse-biased configuration, the positive terminal connects to the n-side and the negative terminal connects to the p-side. This applied voltage increases the depletion region's width, effectively blocking current flow. Only a tiny leakage current passes through. At high reverse voltages, the junction may experience breakdown, either through avalanche or Zener breakdown. This state creates a robust barrier that prevents significant current flow, making reverse bias junctions crucial in creating electronic switches and protective circuits. A tunnel diode is a fascinating semiconductor device characterized by heavy doping and quantum tunneling. Unlike conventional diodes, the depletion region in a tunnel diode is extremely thin, allowing electrons to tunnel across at very small forward bias voltages. This unique characteristic creates a region of negative resistance in its current voltage curve, making tunnel diodes exceptional for high-frequency oscillators and amplifiers. Quantum mechanics plays a crucial role here, enabling electron movement through barriers that would typically be impassable in classical physics. Zener diodes are specially designed to operate in the reverse breakdown region. They feature a sharp, well-defined breakdown voltage called the Zener voltage. When reverse biased and the Zener voltage is reached, the diode begins conducting in reverse, making it ideal for voltage regulation. This unique property allows Zener diodes to maintain a constant voltage across their terminals, making them invaluable in surge protection and voltage stabilization circuits. They transform what would typically be a destructive electrical phenomenon into a useful electronic function. Photodiodes are p-n junction devices specifically engineered to convert light into electrical current. Typically operated in reverse bias, these fascinating components generate a photocurrent when exposed to light. When photons strike the depletion region, they create electron-hole pairs, enabling current flow. This mechanism makes photodiodes essential in light detection applications, including optical communication and photosensing. They essentially translate light energy into electrical signals, bridging the gap between optical and electrical domains. Light-emitting diodes, or LEDs, represent a remarkable semiconductor device that produces light when forward biased. As electrons and holes recombine at the junction, they release energy in the form of photons. The color of emitted light depends on the semiconductor material's energy band gap. LEDs have revolutionized lighting and display technologies due to their efficiency, long lifetime, and versatility. From indicator lights to sophisticated display screens, LEDs have transformed how we use and perceive light in electronic devices. We have reached the end of this video today. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.